All right, let's start looking at differentiation. All right, let's make some opening statements. Some of these opening statements might not be very clear, but as we progress in the lesson, I hope that it will make more sense to you. Now, we'll start up by saying that differential calculus deals with finding the rate at which one variable changes at a particular instance with respect to another. So from that statement, we know that differentiation comes under calculus. So in a sense, we're now starting calculus. The second statement is that differential calculus is the study of the properties of the differentiation of a function, of the derivative of a function. And differentiation is the process of finding the derivative of a function. So again, differential calculus is the study of the properties of the derivative of a function, and differentiation is the process of finding the derivative of a function. So what is the derivative of a function? The derivative of a function is the slope or steepness of the function. The derivative of a function is the slope or steepness of a function. All right, and from your knowledge of coordinate geometry, you know that once we're talking about the slope or steepness of a graph, what we're basically talking about is the gradient. All right, that gradient is a measure of the amount of steepness. So once you're talking about the slope or steepness of a function, essentially what you're talking about is gradient. So differentiation, derivative of a function is actually the what? The gradient of the function. So the gradient of a function is, the gradient of a linear function is a constant, and the gradient of a curve changes along the curve. So the gradient of a linear function is a constant, and the gradient of a curve changes along the curve. This is something that we should know. We should have known from CSEC. Now, the gradient at any point on a curve is equal to the gradient of the tangent to the curve at that point. Also, that is something that we should have known from CSEC. All right, let's have a look at the difference quotient. All right, suppose we're given some function y is equal to f of x, or we're given a function f of x, and we are to find the gradient at any point a on the what? At any point a on the graph of a function. All right, so the x coordinate at a is c, and the y coordinate is f of c. All right, so a is the point, c f of c. So what we're going to do is that we're going to select another point on the curve y is equal to f of x. All right, and that is the point b. All right, so we just selected the point b, and such that b is a point that is close to what? A. The x coordinate at b is c plus h, and the y coordinate is f of c plus h. All right, let's draw a straight line connecting or passing through a and b. So let us find the gradient at a. All right, first of all, let's start by finding the gradient of AB. All right, so so by looking at the graph, we can see that the gradient of AB, and that's m, would be equal to y2 minus y1 over x2 minus x1. All right, so y2, let's use the coordinates at b to be x2 and y2. We have what? Y2 is c plus h minus y1, sorry. All right, that is wrong. Y2 is f of c plus h minus y1, which is f of c. And this is over what? X2, which is what? C plus h minus x1, which is c. So what we can see is that m, the gradient of the line AB, is equal to f c plus h minus f of c, and this is all over h, because c minus c is 0, so it's all over h. Now what happens as h approaches 0? As h approaches 0, the distance here is actually h. H is the horizontal shift. So as one can imagine that as a gets smaller and smaller, the point A is going to come closer and closer and closer to A. Now, if A gets so small um, so that we cannot distinguish the point, so that the line AB or the points A and B become indistinguishable, meaning that A and B are so close it's hard to determine which point is what. At that point, the gradient of AB approximates the gradient of f of x at A. Alright, so as h approaches 0, the gradient of the line AB approximates the gradient of f of x at A. In other words, the gradient of f of x at A is the value m approaches as h approaches 0. Alright, and from definition, the gradient of f of x at A, by definition of limits, is m is equal to the limit of m, which is f of c plus h, minus f of c all over h as h approaches 0. Alright, so the gradient of f of x at A is the value m approaches as h approaches 0. Alright, and that is the very definition for limits. The value m approaches as h approaches 0 is another way of saying the limit of what m as h approaches what 0. Alright, and it is this formula for gradient, which is the first derivative, that is called the difference quotient. All right. All right. Where does a derivative, the existence of a derivative? Well, the derivative of a function, remember derivative is sort of like large another way of saying what the gradient of a function. The derivative of a function does not exist at at any type of discontinuity. All right, we looked at discontinuity in the previous chapter. There is what point discontinuity, jump discontinuity, and infinite discontinuity. So the gradient of a function does not exist at any type of discontinuity. gradient of a function does not exist at a cusp of a function, and the gradient of a function does not exist at a vertical tangent line. All right, definition. Now, the derivative of a function f of x at any point x is the slope of the tangent to the function at x. It is defined as f prime of x is equal to the lim of f of x plus h minus f of x over h as h approaches 0. So the derivative of a function f of x at any point x is the slope, and another word for slope is gradient, of the tangent to the function at x. This is defined as f prime of x is equal to the limit of f of x plus h minus f of x over h as h approaches 0. Notation for derivative. All right. So for first derivative, the notation for first derivative is f prime of x dy by dx y prime or y1 of x. All right, that's y1 superscript 1 in bracket of x. For second derivative, the notations are f double prime x d2y by dx square y double prime and f superscript 2 of x. Now let's have a look at finding derivatives using first principle. All right, so that's another way of saying finding the derivative or the gradient function using the definition. All right, so this says let f of x be equal to c, where c is a constant. So that's another way of saying f of x is equal to, let's say, 3, or y is equal to 3. And if you remember anything from graph, f of x is equal to 3 or y is equal to 3 is a horizontal line that passes through 3 on the y-axis. And also, if you should remember anything from CSEC, the gradient of a horizontal line is equal to 0. So let us see what differentiation says about the gradient of a function f of x is equal to c. All right, first of all, f of x is equal to c, and f of x plus h is also equal to c. And the reason for that is um, f of x is saying anywhere in f you see x, you're going to take out x and put what? X plus h. Sorry, f of x plus h is saying anywhere in f of x that you see, anywhere in f that you see x, take out x and put what? X plus what? H. But there's no x in f because f is equal to c, which is a constant. Now, by definition, f prime of x, which is the first derivative, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so let's finish that on the next page. So therefore, f prime of x would be equal to the limit as h approaches 0 of c minus c over h, which is the same as saying the limit as h approaches 0 of 0 over h, which is the limit as h approaches 0 of 0. All right, and the limit as h approaches 0 of 0 is equal to 0. So if f of x is equal to c, f prime of x, which is the first derivative, would be equal to 0. All right, so some facts about f of x is equal to c. Well, for one, f of x is equal to c is a horizontal line. I already mentioned that. F of x is equal to c is the equivalent of saying y is equal to c. And the gradient of a horizontal line is 0. I mean, as we just shown, the gradient, which is what f prime of x, is equal to 0. The gradient of a horizontal line is 0. So one was from what knowledge of coordinate geometry, and the other one is from differential calculus. Now, when we differentiate a constant, we get 0. So we differentiated y is equal to, differentiated f of x is equal to c, which is a constant, and we got 0. So when we differentiate a constant, we get